So today I'm just going to talk about convolutional neural networks and their application to handwritten digit classification. So I will first just start with an overview of our goal. So as you can see, these are a bunch of handwritten digits, which I'm sure as people, if you see these, you immediately recognize that they are numbers and what numbers they are. This is a lot harder for a computer to do, and we are going to essentially use a convolutional neural network to classify images like these as 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the data set that we're going to use is called the MNIST dataset that was published as part of this paper in 1998. It contains 60,000 training samples and 10,000 testing samples, where each sample is a 28 by 28 grayscale image of a hand-drawn digit between 0 and 9. And these are all written by high school students and employees of the United States Census Bureau. So the current state-of-the-art system on this was released in a pre-published paper in 2020, which has an accuracy of 99.84% on the test set. So it classifies 99.84% of those 10,000 samples correctly. But this has 1.5 million trainable parameters, whereas the network that I'm going to show you in the demo is about, this is about 20 times larger than what I'm going to show. So firstly, what is a convolutional neural network? Essentially, it is a class of neural network that's adapted specifically to 2D and 3D input data. So here you can see we have a 3D image of a car that has 3 channels for R, G, and B color values. We then have a feature learning stage, which is the convolutional section that through a series of convolutions and proving that I'll explain now, we end up with a final sort of feature map that we then flatten out and then can feed to a traditional artificial neural network that then can perform classification to then say that this is a car, a truck, a van, bicycle, or whatever. And in our case, we'll be doing digits. So from a relatively complex input, we can then deduce some interesting things. So the first part of a convolutional neural network is the convolution layer, which essentially, given a 2-dimensional input like this, we have something called a kernel, which then has parameters that can be trained. So you can see here this 1, 2, 3, 4, 5, 6, 7, 8, and 9. These will be replaced with weights that can be adjusted by the network during training. So that is how it will then learn to classify. So we essentially take this kernel and we convolve it with this input by passing it over this blue block in the first case and doing the dot product to get a value of 31. So you say 1 times 1, 0 times 2, 1 times 3, 0 times 4, so on, and add them all together. We then shift this block 1 place to the right and do the same thing to get our value for the second cell. We then shift it again and so on until we've covered the whole input to produce our feature map. And through this concept, we can basically apply a simple kernel that only has 9 trainable parameters to a image of any size and apply what we learn across an entire image. So this makes them a lot more scalable and then artificial neural networks in the case of 2D data. And then by cascading a bunch of these layers together, we then can build up more and more complex features to then detect more and more complex things in our input. So this is just an animation of that convolution process that I explained earlier. So this is a standard convolution using a stride of 1, which is how far the kernel moves over in each for each convolution. here, in the second image, it uses a stride of 2, so you can see it jumps over by 2 each time. And then in the last image, we add padding to our input so that our feature map dimension stays the same as our input dimension. And this is useful if you want to build really deep neural networks, because, as I'm sure you'll notice, the input to the next layer gets smaller and smaller, so eventually we'll run out of an input to then classify. So we can do this to then maintain our feature map. And then we can also have multiple filters, and multiple channels in our input. So in the case of the car example, we have 3 channels, red, green, and blue. Then each filter has weights for each channel, which then get convolved and all added together to then get our values in our feature map. And if we have multiple filters, we just do this multiple times to get multiple feature maps that we then stack together to then feed to the next layer. We also have things called pooling layers that we use to perform dimensionality reduction, which is used to decrease computational complexity and also to prioritize dominant features. So one of these is max pooling, where we take the maximum value in a kernel area. So here we take 9, 2, 6, and 3, which then gets transferred to our feature map. And the useful thing with these as well is that they don't have any trainable parameters, so it's a simple operation that can be used to just perform noise suppression and then reduce computational complexity over time. There's also another pooling technique called average pooling, where you take the average of these values rather than taking the maximum, but max pooling tends to work better. And then lastly, the dense layers that we feed our flattened feature map to in the end is the same as a traditional artificial neural network. So we have our inputs and branches. Each branch has a weight, which then gets multiplied with input and summed together, which then feeds into the neuron. This value then passes through what is called an activation function, which is used to add nonlinearity to our models. And then at the end, a bias gets added so that our model still works when we have all 0 inputs. So the activation function that I'm using was called ReLU, which is a rectified linear unit, which is essentially just a straight line pass through on when the value is positive, and on negatives it's 0. So this is generally a good choice in the beginning for an activation function. It performs well for a lot of different problems, and it's the most common activation function in convolutional neural networks. And then I just wanted to discuss oneheart encoding, which basically our classes that we're trying to classify at the moment are digits from 0 to 9, but this is quite a difficult relationship for the network to learn. So we do something called oneheart encoding, where we have a vector of 9 elements, and we put a 1 in place of the index of our class. So you can see here, in the case of 7, we put 1 in at index 7 to then transform our output class to a oneheart encoded vector. And this also works for if we have classes that aren't actually digits, so like with car, truck, bus, whatever, the neural network can then relate that to numbers, which it can then learn. And then lastly, we have a softmax layer that actually does the classification, where for each of our outputs, we essentially compute a probability distribution over our output classes, which then sums to 1. So then on our output, we get the probability for each class of that being the class of the input. And then lastly, how we do training is we use something called categorical cross-entropy loss, where we have our predicted output from the network, and the actual value. So in our case, the true value will be 1 for the class that we want and 0 for everything else. And our predicted value will be what the network will try and get as close to 1 as it can. So we then compute this loss function over all of our training examples to get an average, and then we tune the network parameters to then try and minimize this loss. And in doing so, our network will then learn how to do classification from example inputs. And fortunately, if you don't understand any of this, Keras does all of this for us. So you don't actually have to understand any of this to be able to do deep learning with convolutional neural networks. So I will then just switch over to my code. Okay, so I just have my code running in a Google Colab environment, which is essentially a free service from Google that allows you to use their backend services to train machine learning models for free. And it comes with all of the necessary machine learning frameworks pre-installed. So you can see here we import Keras and everything else we need to do our training. So I firstly just link it to Google Drive so we can actually save our models once we've trained. Keras also has the MNIST dataset that I spoke about built in, so we can just load that directly from there. So then we have our training, our X training and our Y training, and our test data as well. We can then preview the dataset to see what it looks like. So here you can see just some examples of what the data looks like. So here we have a 5, a 0, a 4, a 1, also a 5 that looks kind of like a 6. So you can see some of the data isn't perfect. So it is quite a difficult task. We then prepare the data by normalizing it, which just makes it easier to learn for the network. And also do the oneheart encoding that I mentioned earlier. We then build our model using Keras. I'm using a model that's defined in the literature called LeanNet5 from 1998 that was built for document recognition with some slight adjustments. So to build our model, it's pretty simple. So we just instantiate the model from Keras, and then we can just add in layers to that, and then run it, and Keras will give us a summary of our network. So we don't need to code any of the actual convolution functions or anything. Keras does it all for us. So you can see we have 81,000 trainable parameters as compared to the 1.5 million of state-of-the-art. So then to train our model, it's as simple as just specifying our input and our examples, saying what we want to do. So we want to maximize our accuracy on the training and the validation set, and we save the model that gets the best validation set accuracy, which is 10% of the training set that we just use to evaluate the model while we train. So if I run this, it will run for 2 pass-throughs through the training set. So we split our training set into batches of 128 samples at a time. So that means that we train for 422 steps. 422 times 128 is then the 60,000 samples minus the validation set. And you can see that Keras is now training, and you can see our accuracy is already climbing from 67% to 92% on the training set after only 2 training runs and about 20 seconds of training time. So it then saved our model to Google Drive. you can see that it has a 97% accuracy on the validation set, which is quite good. But I'm just going to load a model that I pre-trained for 200 epochs using GPU acceleration, just to demo that for if you do have more time to train. So we can then evaluate our model on the training set and the test set, which we do using model.evaluate. It's just taking its time. So you can see we got a training accuracy of 99.93% and a tested accuracy of 99.44%, which I think is about 0.4% off from state of the art with a pretty simple network. We can then take a look at what our model is actually a bit more fine-grained performance by looking at something called a confusion matrix. So here we can see the true value of the classes, so against the predicted values from our model. So you can see in the case of a true value of 9 and a predicted value of 4, there were 6 that our model predicted were 4s, but they were actually 9s. So we can take a look at, say, for example, in the case of a true value of 5 and a predicted value of 3, there's 4 that were misclassified. So we can take a look at that to see what our model sees. So here, these are actually 5s, but our model thinks that they're 3s, which is kind of understandable because they are pretty bad versions of 5s. This is kind of just a hook. And yeah, so we can use this to kind of see where our model's lacking and then try and improve its performance. We can then compute something called precision, recall, and F measure. Precision is basically the chance, if the class is a 9, what is the probability that our model will get it right? So we get 99% on all of the classes, but 9 does slightly worse than others. And recall is how many true classes we actually got of those. So it's a bit lacking on 9, but overall it's still pretty good. Then lastly, we can just take a look at the things that our model got wrong. So out of the 10,000 samples, it got 55 wrong. So you can see here, this is a 2, but our model thinks it's a 7. This is a 6, but our model thinks it's a 0, and so on. Some of these aren't really even distinguishable to people. So this is apparently an 8, and so on. So in a few minutes, we were able to produce a model using Keras that got pretty close to state-of-the-art performance on the MNIST dataset with pretty little effort. So that's sort of the power of these machine learning frameworks. And also without needing to understand much of the background computation that's happening. Yeah, so that's everything from my side on convolutional neural networks.